Hello. So today we are going to look at binary search in as much details as I can. And so let's start off. So just the definition of binary search is it's a kind of divide and conquer algorithm or a method for solving problems. And basically the way we go about it is we solve a problem, we simplify a problem by dividing it into smaller parts, and then we conquer each part, and then after that, once we solve each sub-problem, we kind of combine them. So that's the divide and conquer category that binary search is part of. Binary search can even be more, we can be even more specific and say that it's decreased by half and conquer, because every time we chunk the size of the problem by half and then solve it. And so the canonical usage or the original usage of binary search is when we have let's say an array of or just a sorted sequence, right? Let's call it, for example, X, or let's say just an array. So it's when we have an array, let's say, that is sorted, of course. That's the usual description of a problem that is solved by binary search, and we are looking for some target element in that sorted sequence. And usually what we are looking for is just finding a position in that sorted sequence, right? And so the way binary search solves this problem is by keeping track of a range within the array that we are certain that if the target value we are looking for is at all in the array, we will find it in that range. And that range is shrunk by comparing to the middle of if this is the array and we have the middle here, the goal is to keep shrinking the interval at which we are looking, right, using some probe function. And so initially the range is the entire array, and then the range is shrunk by comparing its middle element to the target value, and we decide, depending on using that comparison, whether to discard the half of that range. And the process continues until either we find T in the array, the target value in the array, or the range in which the process, the range basically that we are keeping becomes empty. And so with this method, because we are halving every time, halving the range we are looking for until it becomes empty, or maybe on the right side, then it's in the structure that we divide something by 2 every time, and the complexity of that is of log n. Whenever you see something that is divided by, that divides the space of the input by 2 on each iteration, then it will take of log n time. And so from just looking at this, you can see that to set up binary search, so this is the usual one, but actually this is not necessary. Like, binary search can be applied whenever you can find a range that has some kind of structure in it, where you could define that range, and then you could define some probing method, which in our case here for this sorted array, you can just check if the middle element is less than target, and that way you can know whether so if it's less, then that means the target is on the right, so you click on the right. And so this is the probing function in this example. And the other thing we need is kind of sorted values. And so next, let's look at just a kind of a pseudocode of binary search that we are used to. So the main idea is that the range that we are keeping, which usually is called low and high, this is the range that we know if t is in the array, it must be in that range. And so what we are going to think about here is our invariant for our loop that keeps looking for the element. So an invariant basically usually means it's just something that, an assertion that the program, so basically there's an assertion that at each iteration of a loop, that condition is always valid. And so our invariant in this case is that if t is in the array, then it must be in range, and this is the range I'm talking about. And so let's just define that or write it in the following way. Let's write that as invariant like this, and it must be in range, which is just an abbreviation of what I wrote earlier. And so our binary search code would be something like this. So we will initialize, of course, our lower and higher values. So for example, in the array case, that would be 0 and n minus 1. And then we would have start our loop, which basically this loop stops when range is empty. And our loop content is that, so basically instead of writing it this way, let me just write it as part of the loop. So we stop if the range is empty. So here, if range is empty, break and report that target is not in the array, right? And the invariant that I mentioned earlier, let's just write that here. That's the usual way you write an invariant, is in the next to the loop. And so invariant of this loop is that it must be in range. The value target, if it's in the array, it must be in that range, which is low, high. And we compute the middle element. And then we use m, or middle, as a probe function. Basically, probe means just something that will help us decide whether to go left or right, to divide the range by half. And then here, if t is found, which means if t is found, break and report its position. Otherwise, just use this mid to go left or right to change the values of the range. And so this is all a binary search does. The tricky part is doing the implementation without any errors. So now let's just try to make this pseudocode here more concrete. And so the first thing I'm going to look at is this must be range. What does that mean here? So we have this thing that says must be range, which is the invariant, and this is just that basically t must be in or not in the array, right? That's what this means. Now the next thing we'll look at is what is this if range is empty? How can we change that? And so the range is just equal to lower and high, right? And so, in the higher position, or left and right, if you want. And then, so when is that range empty? This range basically is empty when the lower value is bigger than the higher value, right? If they are equal, then there is one element. But if it's bigger, let's say lower is 3 and higher is 2, then, well, you don't have anything in this interval, right? But if let's say it was equal or bigger, let's say it was 3, then we have element 3 in that interval. If it was 4, then we have element 3 and 4 in that interval. Okay, now how can we compute the middle element? That's also part of the pseudocode. So compute mid would be, the middle is just high plus low divided by 2, right? To compute the middle of, let's say, 0, 4, right? We just say 0 plus 4 divided by 2, and the middle is just 2, the element at position 2, right? Now the other part of this is use mid as a probe to divide the range by half. And so just the part that says use mid as a probe, how can we make that concrete here? So that means just we need to make a decision depending on the value at mid. And so in our case here, what we are going to do is we can just, so if array mid is less than the target value, we are going to do something. And if array mid is equal to t, we are going to do something else. Let's call this action A, and let's call this or let's say, let's just call this A and B. So here we will do A, and here we'll do B, and here the other thing we'll do C. And that this is basically if is bigger than t, then do something else. Now we need to find what we need to do here. So if the array at the middle position is less than, let's say we have this, and we have this mid element, and we know that, and we are looking for t, and this is a sorted sequence, right? And so if the array at mid is less than t, let's say t is 8, and the value at mid is, let's say, 3, so it's smaller. So we know that 8, since this is smaller than it, that means we need, if we go left, we will find only smaller values than 3, which will be still smaller, so there is no chance of finding something equal to 8, and so we need to go right, right? And so go right. And so this means here, what we need to do is go right. So that's action A here, go right. So what does go right mean? So go right means go to this interval, right? And so at this point, 0, we will initialize low to 0 and high to n-1, and so they would be here. And so high will stay the same in this right interval, but low will now become the value. So we know it's less, right? So we know it's not equal, so there is no point in going to the middle. And so the range that we are going to look at is just after the middle. So that means that low is here. To look at this range, we need low to be here. And so that means that to go right, we need to say that our lower value will become mid plus 1. And so that means that here, what will change is say low equal to mid plus 1. Now the same thing happens when it's bigger, so a similar thing at least. So what happens when it's, let's say, what if array mid is actually, so let's say array mid is actually 3, but the target we are looking for, let's say, is 1. And so this is bigger, right? So if we go right, we'll find only bigger values that will be certainly bigger than 1. And so we need to go left. to have any chance of finding the value. And since we know that 3 is different than the target, there is no need to keep mid in the range. And so what we need to do is go just the element before mid, and from low to the element before mid, right? And so our lower value for the new range will stay the same, but the higher value would be mid minus 1, right? And so here what we are saying is the action we need to take here is go left, right? So this is the left range. And so going left means just change the higher value, change high, don't keep low as it is. And so changing high to what? To just the value before mid, as we said. And so that's mid minus 1. And so going left means just doing low equal to mid minus 1. Now if array mid is the target, let's say we are looking for array mid is equal to 3 and we are looking for 3, so we find that it's equal, well, we are done, just return position mid, right? So just at this point just say position is equal to mid that we are looking for and exit or break out of the loop, right? And so now we have this we have the rest of this probe portion, and we just also defined concretely this. Let's just write the full algorithm then. And so the full thing is we will initialize our low value to be 0, and then initialize high to be the length minus 1, which is the last index, and loop here until, and have the invariant, still keep the invariant that it must be in the range low and high, if at all it's in the array. And then if lower is bigger than high, then we have an empty range, so we didn't find anything, so say that the position is minus 1 and break or return or whichever exit method you want to use, and then calculate the mid, compute the mid, which is just low plus high divided by 2, and then check if array mid is less than the target we are looking for, then then go right, which means that low is going to become mid plus 1, else if it's equal, then you can do these in any order you want, it's the same. Then at this point we need to say that we found it at position mid and we exit. Otherwise, if it's bigger, then as we said we go left, and so that means we assign high to be mid minus 1, and that's pretty much the translation of the pseudocode that we defined here. So just to get an idea of how efficient this is, so I said that the time complexity, so yeah, I didn't mention exactly what the time complexity is here, but so the time complexity of binary search is of course of log n. And this is basically because at every step of the algorithm here we divide the range by 2. So we keep dividing the range by 2, and whenever you do this, then you will get, the loop has to end after log of 2n time, and so time complexity is log of 2n. And just to get a rough idea of how powerful this log of n space, if you had, let's say, a dictionary or a book or a phone book of million names, or a dictionary of million words, right? So if you have a dictionary of 1 million words, then using binary search you could find the exact word you are looking for, or if it's a phone book, you could find the exact person you are looking for in just in around like 21 comparisons. And so you can see if you do it sequentially, it will take you 1 million operations. If you do it using binary search, it would give it to you in 21 comparisons. And so if somehow so if either for a dictionary of words you have them sorted by letters, or a phone book have them the names of all the people in the world sorted by name, then you could roughly, for 1 million person, you could do it in 21 comparison. And even in the entire world, some number of billions, you could probably do it in something around 35, 45 comparisons. So you can see how powerful this is. So what we saw earlier is that applying binary search to an array or a sorted array, but you could actually apply binary search not only for arrays, and I'm just going to call that discrete binary search when it's not applied to an array. So basically an array, actually, what is it? It's just a function, right, from indices to values. That's what an array is, right? You get an array like this, and you have 0, 1, position 2, until position n-1, and you have the values, right? And so the only difference with this new method is that any function that has a domain of indices or domain of integers, right? So you could just have f and then have this is called the domain. Let's call them x, and then the values here would be just f of x. So you need just a function that can be applied, and that is and that you can apply binary search to it. And so what we will be looking for is maybe f of x equal to target, for example. So the only constraint to be able to apply binary search here is that f has to be monotonic. Has to be monotonic. So what does it mean for a function to be monotonic? So basically a monotonic function is just a function between an ordered set, so from the set of integers which is ordered to the values which are the applications of x to these indices. So basically the ordered set is the set of x's to f of x, and you need to preserve the orders, or at least reverse it. What does that mean? Let me just first draw a function. So if you have a function like this, so this is just these are the x values, and so one thing you could have is have it monotonically increasing like this, right? So it always goes up as x goes up, or the other alternative is it always goes down as x goes up. So it's like this. It always goes down as x goes up. You can't have, this is not a monotonic function. So this one here that I've drawn here, this is not monotonic. The other function that we can draw that is not monotonic is like this one is not either, because it goes down and then it goes up. Let's say this function here like this. This is not monotonic because it goes down, goes up, and then it goes down. And so if it has a shape like this, then for example, this one is monotonically increasing, this one is monotonically decreasing, we can apply binary search here. And so you can see here the power of binary search. It's not only can be applicable to an array, it can be applicable to also just any function that has this property. Some people also call this the bisection method. And so you can see here we can also, in the same way that with binary search for the array, we reduce it from looking sequentially on the entire array. Here we will not need to apply f on the entire domain here. We can reduce the number of applications of the function f using binary search here. And so that's very useful because maybe f is expensive and we want to reduce the number of calls to it. Okay, so now that we defined that binary search can be used for any function that is monotonic, so now let's just think about when you have a problem, how can you show that you can solve it with binary search? Since now we said that it doesn't necessarily it can solve more problems than just finding an element in an array. So what types of problem you can see and think, okay, I can solve this with binary search. So so basically let's just define a predicate let's say we have a predicate P, which just can answer by saying true or false, by saying that a statement is true or false, or making a decision about saying yes or no, right? And then let's say we have a search space S that we can apply the predicate to, and the search space has a bunch of values, right? Let's say S1, S2, Sn, and these could be a solution to our problem, right? The search space can be anything, right? And we can use a predicate on that search space by saying, okay, is P of S2 true or false? And we will get an answer, right? So it's still very general so far. And so what we are looking for here is the following. So we can apply binary search to this problem if apply binary search. If for all x in that search space S, the predicate P of x, if it's true, if Px is true, we can deduce that P of y is a true for all y bigger than x, right? So when we apply the predicate to x and find that it's true, that means that P of y is true for any y that comes after x. This of course also means that if Px is false, that implies that Py is false for all y less than x, right? So basically all this means is that if you have the set of applications of P to the search space S, you would start out getting, if it's false here, let's say for x is 1, it's false then, and it's false for x2, so for all these values, and then for some, let's say xi, it's true. That means for all the values bigger than x, once it's true for x, it's bigger for those after it, right? So then if it's false for all the values bigger than x, and once we find the next where the predicate is true, it becomes true. We don't, if you have a problem where x is false and then you find a value x where P of x is true and next value is true, but then you start out getting false, you can't apply binary search to this problem. The prerequisite is that you need to have a structure like this. Okay, so basically that means that if you have this function that you design that can tell you if something is yes or no or true or false, once you start getting yeses, you have yeses after that, and before the first yes that you got, those before it are all no. We will see on examples. This would be more clear on examples. And so with this, what binary search will help us find is the first x, or the first position where it starts becoming true, and the last position where it's false, where the predicate is false. And so basically here, so basically what we can find is the first x where P of x is true, or we can find the last x where P of x is false. And so the main work that we need to do for a problem like this is design the predicate, right? This is the central part of the algorithm. And so let's first take as an example the original problem where we had an array, a sorted array, and we wanted to find target T in array. We want to find the position, right? And so to do that, to write it in terms of this, we need to design a predicate. And so what can be our predicate here? So let's just reformulate the problem a little bit, right? So what we are looking for here is, with this array, we want to find the index of the first value in array that is equal or greater than T, right? So the first value that is equal to or greater than T, when we find that, let's say, Y, right? So if we find that value, then we could just check if Y is equal to T, then return the position. Otherwise, the value is not in the array, right? Because we find the first value in the array, the smallest value in the array that is bigger or equal to T. So that's either T or T is not in the array, right? And so our search space in this, or our S here, is values of array, and our predicate here is basically whether array of X is greater or equal than target. So does it have this structure? Like, let's check if this structure fits the problem. So let's take an array here. Let's take the following array. Let's take the array 0, 2, 11 maybe, 19, and then 21, and then 55, and then let's take 68, or let's take maybe 65, and let's say here 120, an array like this one. Let's maybe here make this, let's take 45 here. And let's say our target that we are looking for, so it's sorted array, right? And let's say the target we are looking for is 45. And so the indices here are 0, 1, 2, 3, 4, 5, 6, 7. And so if we apply the predicate, which just checks whether it's bigger, or the value is bigger or equal to T, then the result for that would be the following, right? So for 0 is not bigger than 45, and so we have false. 2 is not bigger, we have false. 11 is not bigger, we have false. 19 is not bigger, we have false. Here we have false. 45 is equal, so we have our first true value. This one is bigger, we have true. This one is bigger, we have true. So you can see here, it does fit the structure that we have, right? We have a series of false values followed by a series of true values. And once we get true, like this is sorted, right? Once we determine that it's bigger or equal to 45, those bigger than 45 are definitely, by definition, would have px true, right? And so let's see how can we implement this algorithm. We already implemented it here with the usual binary search on arrays. Let's see how can we apply this kind of discrete binary search to this same problem. Okay, so now let's see how to code this for the array case. So we will use just a general template where you just need to change your predicate when you find the algorithm and when you find your predicate in the specific problem you are solving for. But the general template would be something like this, where we have binary search and we have the lower value, the higher value, and the predicate. And these all depend on your specific problem. But the general algorithm for binary search that you will do is, while low is less than high, calculate the middle element, the middle index. So that's low. This way of calculating the mid instead of high plus low divided by 2 is just a way to avoid overflow. But the general template here is that if the predicate applied to mid is true, then what we need to do is set high equal to mid. Otherwise, we need to set low to be equal to mid minus 1. Plus 1. So why is that? Because the general structure is this, right? So you have false, 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 and then you start getting true values. This is the structure. And so if you find that P of some element is equal to true, what does that mean? So that means either mid is, for example, let's say is at this position. Then in that case, the answer, so basically the answer we are looking for is the first true result, right? Which means the first time we get P of X equal to true, right? And so if the value is true, either it's actually the first, so we need to include the middle, or we are in a configuration like this where we have false, false, false maybe, and then true, 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 like this. And the middle we found, maybe it was this middle here, right? No, actually this can't happen. Sorry. So since we start from so the other possible, so the mistake I made here is not this actually. So if we find middle here, the first value that is true, we need to look at, there is no reason to look at this, right? The values that we will find would be true. That's by design of the predicate function. So the way we need to do is look at all the values before. So either this was the first, or maybe there was another true, like this case here where we have mid here. And so there is no reason to look at these. We know that these are true and this one is before them, but maybe the first true is actually before, and which is the case in this case here, which is this one, right? And so we know that if we find the value is true, we need to look left and we need to include the mid, because the answer may be this one. And so that's why when P mid is equal to true, we are going to say, okay, high is going to be here, because our answer is for sure either this value or anything before it, right? Now if it's false, so if the mid value is false, so configuration like this one where we have let's say false, 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 and then some true start happening. And so let's say our mid value is here, and we want to find still the first true result. So if false is here, there is no reason to look at this portion, right? There is no reason to look at this portion, because we know by definition all those before it would be false, right? All those before false are false, so there is no reason to look here, and there is no reason to look at mid because it's false, right? So it's not true even. But we know certainly that it's after the false value we will find the first true. And so we need to look starting from mid plus 1. And so that means we need to set our lower value to mid plus 1, because that's where we have a chance of finding true. The other configuration that we might have is that maybe it's the last false, right? So maybe it's the last false. Let's say true, true, true. Maybe the mid we found is here. Again, the strategy would be to look right, because the element just after it, that's the true value, right? So that means setting low to mid plus 1. This one we already know is false, so it's not the answer, right? And so this is why we are doing this. And at the end, when we are done, basically where the interval is like they are equal, so there is only one element. So either that answer is what we are looking for, or there is no answer in the array. So we can just check if P of low is true, then that means we can return low. Or we can just return -1, or whatever placeholder we want, what the problem asks to return when there is no solution. And so this algorithm, this is the general algorithm when you want to find the first value that for which P of X is true. Maybe the question you got asked is, instead of that statement is the last value. Find the last value where some predicate is false. At that point, only a slight change needs to happen, which is now we are looking for false values, right? And so when we find that an element is true, that's not the answer, so we shouldn't include min. So we should go left to find something false, and so we should do mid minus 1. And if we find a false, maybe that's the false we are looking for, but we are not sure. The last value is either that or anything after it, but we need to include mid because that may be the answer, so our load would be equal to mid. Okay, so this is the general template. For your problem, you will need to formulate it in terms of this P of X, where we are looking for the first value where P of X is true, or looking for the last value where P of X is false, and then just set your low value and your high value and apply this template here. Okay, so now let's take a look at an example here and apply this method and see if it works. So the first thing we are going to try is a problem on LeetCode called LeetCode 69 square root of x. I already did a detailed video on this problem with different solutions, and so, but here it will serve us as a great example here. So this clearly, like from the get-go, the problem says that it doesn't look like a binary search on an array thing, because the problem says that you get a value x and you want to find the square root of x without doing without using square root, right? And so basically what we are looking for, let's say if the value is 4, so if the input x is equal to 4, the square root of x should give us 2. If it's x is equal to 8, square root of 8 is 2 point something, and so we should round it to 2, right? It's 2.82. So the problem says we should round down to 2. I will come back to this rounding it down because that's important in the final solution. And so does our criteria apply here, which we said that function needs to be monotonic? And here square root of x, it definitely is, because what you have is you have something like this, where you have something like this, and then you have x equal to 1, the square root is 1, and then x equal to 2, the square root is something more around here. For 4 is somewhere around here, for 2 is somewhere around here, so it's kind of a growing function like this, so it's definitely monotonic. You can't have like square root of, let's say, 122 smaller than square root of 189, for example. And so it applies. Now let's just think about what kind of predicate we can design to make this criteria here, where we have a set of false and then we start having a set of true. And let's think about our search space. And so two things we need to define: what is our predicate and what is our search space. So we are looking for the square root of x, right? And so if we have like some kind of value, let's say a multiplied by a is equal to x, that means that square root of x is a, right? And so the predicate that we are looking for, we definitely know that it needs to be some kind of function of a multiplied by a, right? Some kind of function g of a multiplied by e. And so to get it to be a solution to a thing where we have false, 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 true, true, if we want it to be the first value where it's true, if we want that to be our solution, then we can just say P of a is equal to a multiplied by a bigger or equal to x. So that means we will have, let's say with x equal to 4. So we'll try 0, for example, first. Nope. So we'll find that P of 0 is equal to 0, which is smaller than 4, right? And so that's false. And then we'll try 1. Let me just write this down like this. And then we'll try 1, okay? And so trying 1 would say, okay, this is equal to 1, and 1 is less than 4. So still we have false. And then we'll try 2, and P of 2 is 2 multiplied by 2, which is equal to 4, right? So now we have something that is bigger or equal to 4, and so now the value we are going to put is true. And so you could see here, even for 3, it's 3 by 3, that's 6, that's 9, that's bigger than 4, so from there it starts being true. For 4, that's 16, bigger than 4, true, and from there, because it's square root, because it's growing, we will have only true values. And for all values, even so here the range, the problem says it's a non-negative integer, because if it was like having negative integers, we will start having -1 and -2, which is 4, and so we would have true over here. And at that point, it will no longer be solvable using binary search. But this problem says that our interval is non-negative integers. And so you can see it does follow the structure here that we have. And so what we are looking for is the first, what we are looking for essentially is the first value where P of A is true, right? And that's exactly what we did with this template of binary search, and so we can just apply it. The only thing left to do, so we know the predicate now. Now we need to find our search space. What is the search space? So for square root, we know that a square root of x can't be more than x and can't be equal to x, right? You can't have square root of something where it's bigger than it. Like for 8, you can't have square root of 9, right? It has to be smaller. It can't be the value itself. That's because the definition of the square root is that you get square root of x multiplied by square root of x, right? And so right away we know that this the search space that we are looking at, it's basically since we have non-negative integers, so the smaller value can be 0 when x is equal to 0. So we know that it starts out from 0, and we know that it won't go over x, right? So it's right, x is the last value you can have, and you can't even have x like this, right? So we know the search space, we know the predicate, we know the low and high and the p function that will pass to binary search. Now all we need to do is apply binary search. And so just one thing to remember is this caveat here. Okay, so let's just write our function that solves this problem, right? And so the way we are going to solve this is, okay, we just, so definition square root of x. And so what is our low and high value? So it's 0 and high is x. I mean, I could put x plus 1, x minus 1, but I'm just going to go with x. It's still part of the search space. For example, actually, it's part of the search space. This is wrong. It's inclusive, because for x equal to 1, square root of x is equal to 1. So if we not include x, then we won't find the solution, right? And so x is included. It's the last value of the search space, so that's the high. 0 is the first value of the search space, that's the low that we start with. And now we start our template binary search, where we said this, and the first thing we do is we calculate the mid, and that's just low plus high minus low divided by 2. And then we check if P of mid is true. The same way I explained earlier, we go right, and the value maybe is high, because if I define the predicate that we just designed, let's say of a, then it returns whether a multiplied by a is bigger or equal to x, right? And so here, if it's bigger or equal to x, then maybe the middle is actually the value that makes it equal to x, right? But otherwise, we just go left. And so to go left, so here we go right, otherwise we go left. And so that's mid, the same way we did for the template, that's mid plus 1, right? And when we are done doing this, remember we need to check, this is because it's general. In some problem we just return low, but to be more general, the template says we need to check that this low value is return the correct solution. This is actually not P. What I should check is solution. Because otherwise there was no solution and we can return -1. And so what I can do here is just check if low multiplied by low is equal to x, so it was a solution, then I can return that value. Otherwise, for this specific problem, because of this, we might round up or something, right? Because for 2.82 we may be around to 3 or something like that. And so to avoid that, if this is not the solution, then it's definitely the low -1, right? Because we round down. And so you can see here we just plug the template and we can solve the problem here. And so here the only thing that we have to think about is does this fit? Can this problem be solved with binary search? We found that it's monotonic. We guessed that probably it is. We designed the predicate in a way that fits the structure that binary search requires, and now what we need to find is just the first value where the predicate is true, and then we thought about the search space, which is just the start possible value and the value that the solution can't go past that value, and those are our lower and high value, and we plugged that into the binary search template and we found the solution. Now let's just plug this into this lead code problem to make sure that this works for all use cases. So just to conclude this lecture about binary search, let's just go through a couple of key points here. So we have a template for binary search. The essential thing that we need to find is the predicate function and the search space. But before that, we need to confirm that the problem can be solved with binary search using first checking that it's a monotonic function and checking that it has this property where once the property becomes true, it will stay true, and all the way before, anything before that was false, and there is no true before that. And then we can just design the predicate, define our search space, apply the template, and that's pretty much all there is. And the template can help us find two types of things. So for example, first we can find the first value that make the predicate true, or we can find the last value that makes the predicate false, and different problems ask for one or the other. So the one thing to keep in mind is always think about, once you know that it can be solved with binary search, think about a predicate that gives you this structure of false, false, true, true. The other thing is always think about whether, going back all the way to the predicate, to the invariant that we said here about binary search, always think about and make sure that the range of low and high that you are keeping is always, if there is a solution, it's always in that interval, that we never have an interval that potentially may not contain the solution. And another thing to be careful of with binary search is to always test edge cases. Basically, once designed and implemented, test with just one element search space in an array that would be one element array. Test with two elements search space for an array that's two element array. Those often, often in binary search you might encounter an infinite loop, and you can often discover that with these two test cases. And yeah, so that's pretty much for this. Thanks for watching. Pretty much it for this. Thanks for watching, and see you next time. Bye.